Okay, so let's look at making an analogy between mass and charge, like we did for the force between charges and the force between masses. So here is a mass, like the planet Earth. And when you have a little m, a little mass like you, sitting right on the surface of the Earth, what's the potential energy of that little object sitting right on the surface of the Earth? 0 if you let the surface of the Earth be where y equals 0. What's going to happen to the potential energy of that mass as I move it away from the surface of the Earth? Will increase the potential energy. So if you were going to increase your potential energy, what would you need to do? And what is a way that you can go away from the surface? How are you going to get up there? Climb a ladder or some stairs or something. Yeah, perfect. Okay. So imagine going away from the surface of the Earth where y is equal to 0 and your potential energy would be 0. So as a mass goes up these stairs, up those little arrows, up the stairs, what's happening to the potential energy of our mass as it goes up these stairs? It's increasing. So our gravitational potential energy is increasing. It's increasing to something where maybe our potential energy is greater than 0 up here. Now let's look at a charge, like a big positive charge. Now we always use a positive test charge to describe everything about charges. We always use our test charge. So if you were to put a positive test charge, so here's our PTC, we would put that right there, and I were to move it out away from that positive charge, so there's my PTC. I'm going to move it over there. Is it going where it wants to go? Yes. Okay. Is it easier to climb stairs or to go downstairs? Go down the stairs. So when you go down the stairs, are you going to a higher energy state or lower energy state? You're going to a lower energy state. Everything wants to naturally be in the lowest energy state. My high school science teacher, because I say science because she taught me physics, chemistry, and biology my senior year, she would always ask us like about our room, and I always remember this. Like, the lowest state of energy of your room is the bed is unmade, your clothes are on the floor, the drawers are open. I mean, because it doesn't take a lot of energy and a lot of effort to like put those things away compared to not. So lowest state of energy is like disorder and messy and low energy. That's where everything likes to be, in a low energy state. So by going away from this positive charge, is it like we're going upstairs or downstairs? Downstairs. So a positive charge is like the top of the stairs. Okay, so let's draw those stairs. Going downstairs. So this would be if our positive, our positive test charge, if it goes up, what's happening to the potential energy then? That's the direction of an increasing potential energy. And it's not a gravitational field anymore, but it's an electric field. So what kind of potential energy do you think this is? Electric potential energy is increasing. So as that PTC, positive test charge gets closer and closer and closer, it will have an increase in potential energy. There will be an increase in electrical potential energy. Now let's look at a negative charge. And our positive test charge, PTC. When I let it go, which way will it go all by itself? Towards my big negative charge. So is it going to a higher energy state or a lower energy state when it goes towards the charge? Lower energy state. So how would the stair steps work? Going down. So it would be like you have stair steps, or our negative Q is at the bottom of the stair steps. So our positive test charge, or our positive charge, our PTC, as it goes up the stairs here, what's happening to the potential energy? Yeah, we have an increase in electric potential energy. Okay, so as we change potential energy, like when you climb stairs, you're doing work. Don't you use some of your energy to make yourself go up the stairs? So there's work being done. So we can relate the increase in potential energy as being related to the amount of work done. And work is force times distance in the most simple terms ever. And that would, if it's your body, that would be mg and d would be y. Do you remember that from last semester? Okay. Now, this isn't a Earth mass scenario, but it's a charge scenario. And the best way to derive the electric potential energy equation is to use calculus and take an integral. But this is not a calculus-based class. So I'm going to do it in a very rudimentary, rough way. And one day, if you've had enough calculus and you keep taking physics, then you'll get to see the real way. But I'm not going to do that today because you can take AP Physics C and join me for that later. Okay, so the electric force then between my two charges was what? K, Q, Q. I'm going to use a big Q and a little q because I have a big Q and a little q. How about that? Over r squared. And maybe I move at a distance of r. Maybe I move it from touching each other to some distance really far away from each other. So what's going to happen? Technically need those guys in there. We'll have K, Q, Q over R. I lost the absolute value signs because I need the sign on the charge so that the sign for the potential energy is correct. Because if we go closer to a negative charge, a positive test charge would lose potential energy, so the negative will mean something to us. So I need to include the sign of the charge. So the electric potential energy, and again, this is a very rough way to derive this. So don't have some argument with a professor or a TA in the future about they're not deriving it the right way. Ms. Howell did a very rough, brute force, hand waving. It's okay. Way to solve it. All right, so K, Q, Q over R, or Q1, Q2. It doesn't really matter which one however you want to write it. I'll even write it with the Q1 and Q2 for you. Same thing. So the electric potential energy, that's what this guy is. And K is our Coulomb's constant, which is about 9 times 10 to the 9. Q's are our two charges. R is the distance between them. Charge will be measured in coulombs. Distance is measured in meters. And what is potential energy measured in? Joules. Very good. Now, if you are going to change your potential energy, you might climb some stairs. So if here are some stairs on the planet Earth, y equals 0, and here you are, and you're gonna walk up some stairs, and you're gonna actually be here, or maybe right there, or maybe right there. Will you have a potential energy when you climb those stairs? What if you're not standing there? If you're just not here and this is just an empty space, is there like, could you go stand on that stair? If you did, would you have potential energy? Yeah. But you're not standing on the stair right now. But there is this potential for potential energy. Where potential means like the possibility, like it could happen. So we can have potential for electric potential energy. And I'm sorry for the nomenclature here. We don't describe the gravitational potential because it's just not a useful calculation. But describing electric potential, the potential for electric potential energy, that is actually a very useful calculation. Turns out it's our voltage. And you probably used some voltage today, whether or not it was charging a device, the device that's using some of the voltage in your pocket right now. The overhead projector thing is using, we all enjoy some 120 volts from our outlets and things like that. So voltage is really a common value, where gravitational potential is not really useful. So this potential for electric potential energy. If you've got a charge, like a big positive Q here, and it's like at the top of the stairs because it has a positive charge would have the most energy there, but there's not a charge sitting on the stair step. Could we put a charge on that stair step? So there could be, in that spot, there could be energy. So right now, with nothing in that spot, there is the potential for electric potential energy. Or there is some joules per coulomb available. Joules being K, Q1, Q2 over R. Joules divided by coulomb, what's that going to be? A coulomb is a measure of charge. So maybe if this is Q1 and I'm going to stick a Q2 on there. So then we'll have K, Q over R. That is the electric potential. Okay, so this is our electric potential. Electric potential. This is the charge measured in coulombs. This is the distance from the charge. So where is that stair step? And that would be in meters. K is Coulomb's constant, which is about 9 times 10 to the 9. Now we have to deal with units. It is joules per coulomb. And a joule per coulomb is the same thing as a volt. And you can use capital V for a volt, which gets all kind of crazy seeming. simply the electric potential. This describes how much energy is available at a distance from a charge. It's not necessarily the amount of energy that is there because there's not a second charge. Okay, so let's look at a big positive Q again. So here's my positive charge, and I'm going to draw some stair steps. So if I've got this idea of concentric stair steps, concentric circles or spheres really, because it's three-dimensional all the way around, each one of these red circles, red doesn't really mean anything, but I just use a different color, is an equipotential line. Meaning that at any place on this circle, at any level right there, that's a stair step, and that has all the same voltage, all the same joules per coulomb. Now again, if we use our positive test charge, our PTC, which way would a positive test charge move if we were to release it? Away from it. So that means that my electric field would be directed away from my positive charge here. Electric field. Electric field. Now where is the high potential line and where's the low potential line? Okay, so our electric field line is running from where to where? From high electric potential to low electric potential. So this is the relationship between electric fields and electric potential. So each one of these levels has the same electric potential. The electric field would also be the same at any point on that same level. And I can determine the direction of the electric potential values if I know the direction of the electric field. So far, so good? No, there's not actually anything there. It's not really an orbital, but well, it could be. Let me think about that for just 1 second. So yes, if I have a electron that's at a higher energy state, it's further from the nucleus and it falls back down, it will actually change energy, emit a photon. That's nuclear physics. We will study that a little bit at the end of the semester. Okay, now if I have a negative charge, and I'm just going to use another color. So our stair steps would be similar looking from this perspective, but the electric potential levels, are they increasing or decreasing as I go away from this negative charge here? Or increasing. That's right. Because a positive test charge would be gaining potential energy as we move it away from a big negative charge. Which direction is the electric field around this big negative charge? Towards it. So I have an electric field towards it. Electric field is towards it. Does it follow the rule where my electric field is running from high electric potential to low electric potential? Yeah. Very good. Now, we can relate electric potential and electric potential energy because isn't our electric potential the energy per charge. So our electric potential energy would be the charge times the voltage, or the electric potential. So if you know that this equipotential line, this distance, whatever it is, from this negative charge is 600 volts, and I put a 2 coulomb charge there, how much energy is in the system? If this electric potential is actually, it should be like, if my electric potential at that outer level was, it should be negative 600 volts. And I put a charge of 2 coulombs at that level. How much energy is in the system now? Well, this is where we have to think about, what does zero mean? So why is it negative? Well, if you've got a positive charge, and a positive charge is like at the top of the stairs, go down, 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 to what's the lowest potential you could eventually have? Zero. So this would be like at R is infinity. Your electric potential could be zero. But then, if we're thinking stair steps, what's at the bottom of the stairs? Our negative charge. So can you have a negative potential energy? If this is the Earth and this is y equals 0, so maybe this is the ground level at school. So that's the level that the office is on. Okay, you go upstairs and you're in 2306. Or you go downstairs and you're in the media center. What's your potential energy when you come in through the front door? 0. What's your potential energy when you come to my classroom? Something greater than 0. What's your potential energy when you go to the media center? Some negative number?
For the charge to have negative voltage, wouldn't it have to be more than infinitely away? Because if it is 0 when it's infinitely away,
For a positive charge, when we're infinitely far away, the potential energy is 0. Because if U equals K Q1 Q2 over R, and R is infinity, then you'll have U is equal to K Q1 Q2 over infinity. What's over 1 over infinity?
0.
Approximately 0, so our potential energy would be 0. Now, if these charges were positive, or these charges are negative, or one of them's negative and one of them's positive, is that going to change U being 0? No. What changes is, what does 0 mean? So for a positive charge, a 0 potential, 0 voltage, so if V is equal to KQ over R, and R is infinity, KQ over infinity is also about 0. So if your electric potential is 0, then in terms of a positive charge, that's the smallest potential energy you can ever have. In terms of the negative charge, what would 0 be? Or the largest potential energy. So aren't you losing, like there's a decrease in potential energy as you go downstairs? So if 0, and then you go downstairs, so down here you have some potential energy that's less than 0, then what does 0 mean? 0 potential or 0 potential energy mean for a negative charge? It's the biggest it can possibly be. It's a really hard thing to kind of wrap your head around. And I get it, and I'm sorry. It'll just take a little bit of time, hopefully. We'll work through it. So another way to think about it is if you've got a positive charge here and you've got a negative charge here, and let's pretend like this is infinity. What do they want to do? If I let go of those two charges, what do they want to do? They want to move towards each other. They want to move towards each other. But they are so far away from each other right now that the force on them is pretty small. But as they move closer and closer, what's going to happen to the force? It's going to increase. And it'll increase and increase, and they're moving faster and faster and faster and faster and faster until they collide with each other. But right now, there is this, it's like you have pulled a spring because they like each other. What does that spring want to do? If I have stretched that spring, I'm having to hold it apart. So right now, when I've got those two charges really far away from each other, I'm holding them really far apart. Mathematically, they have zero potential energy. And when I let them go, they're going to move towards each other. When they move towards each other, they should lose potential energy because that's what things do when they go where they want to be. So if you start out with zero potential energy and you're going to lose, then what kind of potential energy you're going to have later? Negative. So for a positive charge, zero electric potential is a very small number. But for a negative charge, zero potential is a very big number. And that's not easy to understand. So I'll let that soak for a minute here. Now, let's look at this electric field that was creating, let's go back up there and kind of look at that electric field. So if I have an induced positive charge, maybe this is a metal sheet and I've turned it sideways so you're looking at the end here. And maybe it's even connected to a wire that goes to the earth. And I have this negatively charged sheet over here. What's this negatively charged sheet going to do to this metal over here? It's going to attract protons, but protons can't move. What can move? The electrons. So it's going to force the electrons to run through this wire, like when we were playing with a Van de Graaff and you touched it and zap, the electrons went through you to the ground. So now we have this induced positive charge here left on the plate, and we have a negative charge over here. And as I get further from this plate, my electric field would decrease, but I'm getting closer to my negative charge, so what's going to happen to my electric field? It would increase. So a decrease and an increase at about the same rate there would give us a constant electric field between the two plates, or a uniform electric field. I mean, it's the same no matter where you are. So if I were to put a positive charge right here, which way would it go? Towards the negative, which is the definition of my red electric field lines there. And what would the force be? F is equal to, for a charge in an electric field, QE. And work causes a change in potential energy, and work is force times distance, and force is QE times D. So could we find the change in potential energy of our charge as it moves through this electric field? And if potential energy is equal to QV, then how can I define the voltage of a uniform or constant electric field? ED. So this has to be a constant electric field. We can have an arrangement of charges. We've done a couple of problems like this with electric force and electric field. So what if we had a Q, a 2Q, and a 3Q at corners of a square? Could you solve for the potential energy, the electric potential energy of this system? Yeah, you could sum up the electric potentials of the pairs. You'd have the electric potential energy of 1 and 2 plus the electric potential energy of what, 2 and 3, and is that it? 1 and 3? Does that take care of all my pairs? So then substitution wise, let's see if this is square and it has the sides of D, then I'd have like K no vectors, no angles. Isn't that nice? Yay! What about this empty place up here in the top right hand corner? Could I find the electric potential at that point? Like, what is the stair step there? What is the level of the stair step there? I've got 3 charges. They're all creating their own stair steps, and we've merged their stair steps. You could think of the 3Q as having steeper stairs than the Q because it's a bigger charge. And you merge them all, and you get a final electric potential. So you could find the electric potential created by the first charge, and the electric potential created by the second charge, and the electric potential created by the third charge. So it would be like KQ over D plus K2Q over what, D root 2? Plus K3Q over D. And just add them up. What if one of the charges was negative? I'd need to include the negative sign and I wind up subtracting it.